Today, I'll present a brief summary of our recent work on speech intelligibility prediction using spectro-temporal modulation glimpsing. In human-human communications mediated by computers and networks, speech signals are often distorted, and they're not perfectly perceived by the listener. Because of that, perceptual evaluation of the degraded or processed speech signals is of a great importance. Speech intelligibility is one of the most critical perceptual attributes of a speech signal and quantifies the degree to which the listeners correctly understand the speech signal. Speech intelligibility is often measured in terms of phoneme, word, or sentence accuracy rate. Intelligibility becomes the dominant perceptual factor in adverse listening conditions, for example, in very low signal-to-noise ratio or SNRs. The intelligibility of a speech signal can be determined by conducting subjective listening tests, which involve a group of typical end users listening to several test signals and identifying the spoken message. However, conducting a subjective listening test is typically extremely time-consuming and expensive. It also requires access to specific equipment which might not be easily available. Machine learning algorithms can facilitate predicting the perceptual effect of different types of distortion and processing on speech signals. An ideal speech intelligibility prediction or SIP algorithm would accurately predict a speech signal's average intelligibility as perceived by a group of listeners. SIP methods are commonly divided into two categories: intrusive or reference-based and non-intrusive algorithms. Intrusive SIP algorithms require a clean or reference version of the signal under test to be provided as the input, while non-intrusive SIP methods do not require knowledge of the clean signal. In this study, we proposed an intrusive monaural speech intelligibility prediction algorithm for normal hearing listeners and evaluated its performance over multiple listening test datasets. Before describing the processing steps of the proposed algorithm, STGI, I think it is helpful to take a quick look at the conventional definition of glimpsing and glimpse proportion. In his seminal work on glimpsing model of speech perception, Martin Cook defined glimpses as those time-frequency regions in which the target signal is least affected by the background noise. More formally, he defined glimpses as the regions in the time-frequency representation of the speech signal where the local SNR exceeds a certain threshold. He showed that the proportion of the time-frequency regions glimpsed, or glimpse proportion, or GP for short, is a relatively good predictor of speech intelligibility in many conditions. This figure shows a block diagram of the proposed STGI algorithm. The algorithm takes the degraded speech signal and the clean time-aligned version of it as inputs. First, a voice activity detector removes the silent frames from the clean and degraded signals. Next, a multi-frequency spectrogram is calculated from the input signals. After that, the spectrograms are passed through a Gabor filter bank to decompose the inputs into multiple spectro-temporal modulation channels. The filter bank consists of 11 spectral and 4 temporal Gabor modulation filters, covering the range of modulation frequencies that are known to be important for speech perception and SIP. The spectro-temporal modulation filter bank is implemented as a two-step procedure: a spectral-only modulation filtering followed by temporal-only modulation filtering. The filter bank's output consists of 44 filtered spectrogram or modulation channels that exhibit modulation characteristics of the associated filters. After that, each filtered spectrogram is divided into overlapping short time segments of roughly 500 milliseconds, and each segment of the degraded signal is compared to that of the clean signal using normalized cross-correlation to produce a similarity measure. Next, the similarity measures are compared to a fixed threshold to detect glimpses. Finally, the overall intelligibility is estimated as the proportion of the glimpsed segments over the entire input. Here, I would like to contrast STGI to conventional glimpse-based intelligibility prediction models, such as GP. First, as I discussed before, traditional glimpse-based models use local SNR for glimpse detection. For example, GP compares the local SNR in each time frequency unit to a certain threshold to detect glimpses in the time-frequency representation of the speech signal. This simple and quite effective approach has one major limitation. The notion of SNR is only defined for additive uncorrelated noise conditions and is not well defined for processing conditions such as reverberated speech or speech processed by nonlinear noise reduction algorithms. Therefore, the application of such methods is limited to additive uncorrelated noise, where the notion of SNR is meaningful and well defined. In contrast, our method uses the normalized cross-correlation between the modulation envelopes of the clean and degraded signals for glimpse detection. Therefore, the application of our method is not limited to additive uncorrelated noise. The second significant difference between STGI and GP is that STGI decomposes the input-to-speech signals into multiple spectro-temporal modulation channels. Analyzing the spectro-temporal modulation envelope of the input signals enables STGI to better account for the modulation characteristics of the masker and the target speech. SIP algorithms are conventionally evaluated using the Pearson and Spearman rank correlation coefficients or their variance. The reason is that the listening test score scale generally depends on the listening test parameters not known to the algorithm, such as the stimuli corpus, subject, response protocol, and scoring method. In this study, we used Pearson and Spearman rank correlation coefficients between the listening test scores and the SIP algorithm's outputs to evaluate each method's performance. We evaluated the performance of STGI along with a suite of state-of-the-art SIP algorithms over 15 listening test datasets. You can find more details about each dataset in our paper and the references in there. Together, the datasets covered a broad range of distortions and processing conditions, including modulated noise, checkerboard noise, gated noise, speech processed by nonlinear noise reduction algorithms, reverberated speech, and speech processed by near-end listening enhancement algorithms. This table shows the performance of the investigated algorithms in terms of the Spearman rank correlation coefficients. As you can see in the table, STGI shows excellent overall performance, outperforming state-of-the-art SIP algorithms in additive uncorrelated noise conditions and overall. Not only STGI outperforms GP in additive uncorrelated noise conditions, but also it extends well to other processing conditions. An interesting observation is the failure of several state-of-the-art speech intelligibility prediction algorithms in the presence of checkerboard and gated noise. These conditions consist of artificial maskers that provide a controlled environment for studying the influence of the spectro-temporal properties of the glimpses on a speech perception. A speech intelligibility prediction algorithm's ability to successfully capture and model such properties can lead to performance gains in other degradation conditions. We note that several successful SIP algorithms, such as WCMI, ESTOI, and SIIB, that have excellent performance across many acoustic conditions, struggle to predict intelligibility in the presence of checkerboard and gated noise. On the other hand, STGI consistently shows high correlation with the intelligibility of a speech in such degradation conditions. We proposed a monaural intrusive speech intelligibility prediction algorithm called STGI based on detecting glimpses in short time segments in a spectro-temporal modulation decomposition of the input speech signals. Unlike existing glimpse-based SIP methods, the application of STGI is not limited to additive uncorrelated noise, and it can be employed in a broad range of degradation conditions. Our results showed that STGI performs consistently well across 15 datasets covering degradation conditions including modulated noise, noise reduction processing, reverberation, near-end listening enhancement, checkerboard noise, and gated noise. The spectro-temporal modulation decomposition of the input speech signals enables our model to account for the modulation properties of the masker and the target speech.